everyone, this is KP the Math G here, and we're here to do another AP Calculus video. Matter of fact, this is going to be the 196th video of, well, all of them that we've done. All of them have been AP Calculus based questions. So we're going to dive right in and get started with this one. I love this problem. Matter of fact, I've been on vacation for a week and I'm back and a little tired, but I'm so ready to go with this problem. It's a very good problem, and I think we need to pay attention to this type of problem. It says that a weather balloon is rising vertically at a rate of 15 feet per second. An observer stands 600 feet horizontally from where the balloon was released. Alright, so if you think about this just for a moment, we're going to stop right here. And we see that a balloon, I don't know if I can write it all down, but this balloon is rising vertically. Uh-oh. Some of my pens do not write. I'm just going to put that one away. It's not writing very well. We'll try it again. The balloon is rising, alright, like this. Alright, so we may have a picture of a balloon there, and it's rising at a rate. Alright, so it's rising vertically. Alright, and usually, a lot of times when we talk about vertically, rising vertically at a rate, now anytime we see rate, we're going to see what that rate is. And since this is associated with y is the distance, but the rate, ladies and gentlemen, is dy over dt. Okay? dy over dt, which is 15. Well, it's okay, so this equals 15. What is that? Feet per second? Okay. So this balloon is rising. An observer stands 600 feet away. Okay? So I'm going to kind of draw this a little bit further down right here. And 600 feet away. Alright. It's going to make a right angle. Alright, and so it's on flat ground, in other words. Not on a hill, but flat ground. 600 feet horizontally. Now, when we see 600 feet horizontally, isn't that going to be the x? How far that is? This is the x-axis, this is the y-axis. So x is having a distance of 600 feet. Okay? It says when the balloon is 800 feet in the air, and so that's the instant that y is, the instant that y is 800 feet. Okay? So this height at this instant, this is a snapshot. You might say this is kind of like a snapshot picture of this balloon. Okay? At that instant that this balloon is 800 feet in the air, find the rate, the angle at which the angle of elevation from the observer to the balloon is changing. Alright, so this is certainly not drawn to scale, but we're going to say then, we're just going to draw the, oh, that's crooked. Okay, I'll try to be straighter. I don't have a straight edge, so we're just going to have to draw. There it is. That's about as good as I'm going to get it. So what are we trying to find? The angle of elevation. This angle of elevation, we'll say, is theta. Okay? And so if we have the rate at which the angle of elevation from the observer to the balloon is changing, this is the angle right here. This could be 45 degrees for all we know. This could be 60 degrees, 75 degrees. But that's not what we're looking for. We're looking for the rate at which the angle of elevation is. So that's going to be d theta over dt. We could find this line of sight, you know, if we wanted to do that. But we have enough information here to do what we're doing. Okay? Now, remember that this y height at that instant is 800 feet. And when we take that snapshot right here, this height is 800 feet right here. 800 feet. Alright? So, let's see if we can kind of come up with some d theta over dt. That's going to lead us into sine, cosine, and tangent. But since we are dealing with this opposite of this angle, this is opposite, and this, remember, this is the hypotenuse, and we don't even have anything related to the hypotenuse here. We're down to adjacent, aren't we? Alright, so opposite over adjacent. Okay, let's look at that. What trig function is going to be, what could we use with opposite over adjacent? Yeah, that's right, tangent. So what we're going to have to deal with is tangent of theta. Alright, tangent of theta is equal to opposite, let me move over, opposite of theta is 800. Alright, so opposite is 800 over adjacent, which is 600. We can reduce that to 8 over 6. We can reduce that even to, what, 4 over 3? So 4 over 3. If you want to leave it like that, you can. So, that's important that we understand, that we find what the tangent of theta is. Alright, but now also tangent theta without the numbers is y over x. X is already given. Now, this is at the instant, this is 800 feet right here. But x is already given, and this is a trick. This is kind of very tricky if you're not careful here. You really need to put down, if there is a fixed number, which this is, 600 is fixed. You're not going to have a change in x anywhere. Okay, you're not going to, your dx over dt is 0. There's no change. So what you can do is you go ahead and make your x 600. Alright, don't put your 800 up here. That's alright. We just needed this. And actually what we really need is all the others. Now there's another one that we need to pay attention to, and that is, because we're going to take the derivative, I want you to understand that we are going to take the derivative of tangent in just a moment. We're going to take this derivative of both sides of this right here. That's what we're going to do. All right. So let's just, before we get it any more in the detail, we do need to know the tangent theta is 4/3. Okay, and then we can get the other. We can get the others later in just a moment. All right. Let me see if we can do a little more to this. Okay. Now, this is well over 600. Let's just put it down here. Tangent theta. We could kind of rewrite this by multiplying both sides by 600. We didn't have to do that, but I'm going to go ahead and do that. So we got 600 times the tangent of theta is equal to y. Okay. We didn't have to. I could have left this 600 right down here and just took the derivative of both sides. The only way we're going to get to d theta over dt is take the derivative of tangent. Now, let's go ahead and go a little further. 600, let's go ahead and take the derivative of this side. Now you got to know your derivatives of all the trig functions. The derivative of tangent is secant squared. When you take the derivative of tangent of theta and get secant squared theta, you got to tack on d theta over dt. Now, we already know that the derivative of the y is dy over dt. We know what dy over dt is. It's 15 feet per second. Alright, so I don't want to flip this over if I can. Maybe I don't want to have to erase all of this. Let's go ahead and flip it over because I do need, well, we might have to flip back and forth. Okay, so let's see. This is d theta over dt. Okay, now, secant squared. We need to find out something about what secant theta is and then turn around and square that. Alright, so what we have here is 600. We're going to find out what secant is, and we know that this is 15 feet per second. Alright, there's that much right there. We already have that far. Alright, so let's find out what secant, and by the way, this is squared. Alright, so we got to find secant. Well, let's put it over here somewhere. Oh my goodness. Let me erase some of it. Okay. Let me see here. We've got to find the hypotenuse to this. And in our last problem, okay, so if we did 600 squared plus 800 squared, we're going to get 1,000 in all. So, this would be z is equal to 1,000. There is a such thing as, put it up here, 3, 4, 5 triangle. If you double the 3, you get 6. If you double the 4, you get 8. If you double the 5, you get 10. If you put a couple of zeros on that, you need to put a couple of zeros on everything else. So there is a 600, 800, 1,000 triangle. 600 squared plus 800 squared is 1,000. Okay? The square root of that is 1,000. Okay? Now, so this is 1,000. Secant, I'm just going to have to erase some of this. I don't want to have to flip this board over. Secant theta. Secant theta is the hypotenuse over the adjacent, which is the hypotenuse, which is z over x. So secant theta is equal to 1,000 over 600. I'm going to take a couple of zeros out, and that's going to make it 10 over 6. Right, like that. I'll just leave. I can reduce that even further if I want to, but I'm just going to leave it like that. Okay? We're looking at secant squared though, aren't we? Because that's secant squared, and all this really means is secant squared. That's really what that means. Well, secant theta happens to be 10 over 6. And I guess I could have reduced that to lowest terms into 5 over 3, but that's okay. Now that's equal to 15. I guess we will flip this over now that we've gotten this down here. Okay, secant is 10 over 6. So secant theta is 10 over 6 squared. Alright, so 600 times 10 over 6 squared. D theta over dt is 15. Let's move this up. Okay. Alright, here we go. I apologize for the lack of room here. Okay. So what we have here, ladies and gentlemen, is 600. It was 10 over 6. Well, let's go back to what we had. Secant squared theta was equal to 15 feet per second. I think I have everything there. If I wanted, d theta over dt. That's right. Now, that's the chain rule. Alright, now equals 15. You leave this out, you don't know what you're doing here. Alright, we did find, now we've got a little room, I can go ahead and do this now. This was 600 feet. Let me just say 600 feet. At the time, that the moment that the balloon is 800 feet, this is going to now be 1,000 feet. Alright, that's what we have here. What we had was 600 squared plus 800 squared. Alright, is equal to z squared. And then when we took the square root of both sides, we found this to be 1,000. Okay? Alright. And so that's what we did. So what we really did right here is 600 secant again was 1,000 over 600 squared. Bear with me. D theta over dt. Let's get something that can write a little bit better than that. I'm running out of ink, I know. So, bear with me again. Let's try it again. 6 over 10, 600, 10 over 6 rather. And I could have reduced that even more. Don't know why I didn't, but okay. I think it's just easier. Once we do this, you'll see why. So 600. Now we've got 100 right here. 10 squared is 100. Well, I guess 6 squared is 36. D theta over dt is equal to 15. We can still reduce that. Well, I don't know if it would help to do that anyway. So let's see what happens. We've got, we can multiply across if we want to. Okay. Let's see if 600 will go into 36. Well, I know it will go 6 times. So 36 will go, 6 go into 36 6 times. 6 times 6 is 36. 6 will go into 600 100 times. Alright, 100 times 6 is 600. We could do that again if we wanted to. 6, 2 goes into that 3 times. 2 goes into this 50 times. So now we got 50 times 1,000, which is 5 with 1, 2, 3 zeros. Count the zeros over 3. D theta over dt is equal to 15. Now if we can take the zeros out right here. Okay, oh, I had it over 3, didn't I? Okay. Wait, sorry. 5. Okay. Bear with me, I know I'm just being a little bit slow today. I drove all day yesterday for about 9 hours, so I'm tired. Both sides, just flip it over. Both sides, just flip it over like that. Okay. Now if I did my arithmetic correctly, I know what d theta over dt is. 15 times 3, 15, 30, 45. Now I think we can reduce that. Oh, let's see. 5 goes into 45 9 times. 5 goes into 500 1,000 times, and that is correct. 9 over 1,000. Now, how do you measure d theta over dt? Well, that's going to be in radians, in terms of radians, and since we are in seconds, radians per second. 9 over 1,000 radians per second. Okay. I believe I've done the arithmetic correctly, and I don't think I made an error in this, but I do believe this is correct. Okay. 9 over 1,000 radians per second. So what does it say? What did we just find? Let's go back over here. It does have, let me go this way. saying, find the rate at which the angle of elevation from the observer to the balloon is changing. So how fast is theta changing? That is d theta over dt. So I want to say we did 9 over 1,000 radians per second. And that's how you do that. So there's a lot involved with this problem, I have to admit. You need to know that the derivative of tangent is, you have to know that's tangent. We set up the tangent. Alright? And I just kind of knew to set this 600 as a constant here. Alright? And I know that this dy over dt is 15. So I already knew that. It was given to us. Alright, we had to find this to be able to find secant squared. So we had secant as 1,000 over 600. But when you had to square that, of course, we reduced it and squared it. Okay? Let's make sure that we did everything correct here. Alright. Bear with me, I know this is a lengthy problem here. Yeah, 10 squared is 100. Alright. And 6 squared is 36. Okay, and that's it right there. And then we reduced that and got it to fit, wait a minute. 50 over 3, did we not? What did I get? What did I do here? Oh, we multiplied that 50 by 100, didn't we? Yeah, plus 3 more 5,000. That does work. So 5,000 over 3 here. Okay. And that does make it work right there. 9 over 1,000 radians per second. Okay. Anyway, that's quite a bit. Derivative tangent is secant squared. We had to square that. We did. We solved for d theta over dt. This is not an easy problem. And needless to say, it's not so hard that we cannot understand. We could have used cosine also. It would have been even longer than this. But cosine and tangent will both give you the same answer. Sometimes, in certain situations, you can use sine. Okay? But in this particular case, it's best to use tangent here. Okay? And that just comes with a little practice. And more and more practice, you get to see which one works the best. Alright, and so there it is. So KP the MFG signing off. Please, if you haven't subscribed, please subscribe to this channel here. I would like to see more subscribers, but if you don't subscribe, it's not about me, it is about you. If you'd like to make a comment, please make a comment. If there's anything I could do better, let me know what I could have done better. I do want to improve and get better on this. If there's something I did well, I mean, well done, thank you. Something like that. If you find that you want to hit that like button, I always smile when I say that. But hit that like button. But then again, this is all about you. It is not about my glory. I don't see glory out of it. I do get satisfaction out of working these problems. And soon, let me see if I can find, I don't know if I have it readily accessible to me. It may be that I do have it. Let me see if I can find the problem that I was working. Yeah, it is here. Let's see if I can find. Okay. I'm not so sure. Yeah, 9 over 1,000. That's right. That's what we got. We got it. 9 over 1,000 radians per second. I just want to make sure that, you know, they're right. No, I do check myself too. I like to see that we're on the same page here. All right, that makes me feel good. KP the Math G signing off. Ladies and gentlemen, have a great day.